Welcome everyone to today's in-depth AI on AI podcast, where we dive deep into managing complex failure analysis workflows using LLM-based planning agents.
Thanks for having us. This topic is fascinating as it blends sophisticated technical algorithms with real-world industrial challenges.
Absolutely. And from a business perspective, these AI-driven workflows are revolutionizing failure analysis in semiconductor fabs, cutting costs, and speeding up decision-making.
Right, especially when you consider the ReACT approach, the integration of LLM reasoning with tool invocation. It's like having an intelligent assistant that breaks down complex queries into actionable steps.
I'd add that the modular design using LangChain and Python is a game changer. It decouples the hard-coded pipelines and makes the system adaptive to evolving data landscapes.
And let's not forget the surprising twist. While many focus on static pipelines, this research emphasizes flexible, autonomous planning that learns from environment feedback. A real eye-opener.
It's interesting how the paper addresses both the technical intricacies and the business impact in semiconductor failure analysis. Could you elaborate on that balance?
Sure, the technical methods include detailed implementations of online replanning and zero-shot prompting methods, which are built upon advanced transformer models like Mixtral, 8x7b, and Llama 3.
From the business standpoint, imagine a scenario where every minute saved in failure resolution translates into hundreds of thousands of dollars in reduced downtime, similar to the 80-20 rule, where 20% of process improvements yield 80% benefit.
Exactly, and the agent's iterative process, using a thought-action-observation loop, mirrors human reasoning while ensuring consistency through plans that constantly adapt to feedback.
This is very much like debugging in software. Each feedback loop refines the system until it converges on a solution, but in this case, it's applied to physical device failures in manufacturing.
I must offer a slightly contrarian view, though. While automation here is impressive, human expertise remains irreplaceable, and incorporating a human in the loop could enhance reliability even further.
That's a great point. Balancing autonomous AI with human oversight seems crucial. How do you see the technical design managing tool interoperability?
The design intricately encapsulates each tool as a Python class with prompts stored externally, making it both modular and maintainable. It ensures that each component, be it a database query or an image classifier, communicates effectively with the LLM.
And in terms of deployment, businesses have witnessed reductions in manual oversight by integrating these systems on cloud platforms like the one Infineon uses. Think of it as upgrading from manual gear shifts to automatic transmissions in a fast-paced race.
Right, the use of structured tools like Elasticsearch for FA job retrieval and Confluence for knowledge management demonstrates practical architectures that can interface with legacy systems in large enterprises.
It's also remarkable that the LLM agents employ short-term memory strategies, ensuring memory doesn't overflow into endless loops, a common pitfall in earlier AI systems.
And let's not overlook the integration of retrieval-augmented generation pipelines, which enrich responses. It's like having a personal research assistant that scours through vast databases in seconds.
That mix of techniques is quite robust. Could someone explain how the ReACT agent specifically improves over traditional static pipelines?
The ReACT agent decomposes high-level queries into a sequence of subtasks. This thought-action-observation loop not only streamlines problem-solving, but allows the agent to dynamically replan if any tool fails or yields unexpected results.
Additionally, using zero-shot prompting here leverages minimal example biases, ensuring that output is primarily generated from real-time context rather than a rigid template, much like improvisational jazz where spontaneity meets structure.
From a strategic perspective, this flexibility translates into higher throughput in analysis labs and enables companies to remain agile even amidst rapid technological changes in manufacturing processes. The approach also includes robust error handling, Anytime a tool fails, it logs the event and either switches to an alternative module or provides a controlled message, maintaining operational continuity.
And humor me, if you will. The iterative nature of online replanning echoes the wisdom of, if at first you don't succeed, try again, yet with calculated modifications at each step that minimize unnecessary resource consumption.
That iterative approach really stands out. Let's shift a bit. How do these techniques directly translate to business metrics?
In real-world cases, companies using similar LLM-based agents have seen failure resolution times drop by up to 40%, leading to optimized manufacturing throughput and significant cost savings.
And on the technical side, the evaluations, even though answer quality scores are moderate initially, demonstrate potential. With prompt engineering refinements and domain-specific tuning, performance could skyrocket further.
The balance is delicate. While highly technical configurations like intent classification and retrieval-enhanced prompts push accuracy, they may add runtime, so businesses must weigh speed against quality.
Precisely, the trade-offs here are akin to financial investment decisions. You decide whether to invest in speed or depth of analysis, much like balancing risk and reward in a portfolio.
I see where you're going, but I think we sometimes over-optimize for speed and lose the context depth necessary for truly insightful failure analysis. A measured approach is key.
Interesting. So it's a nuanced trade-off between rapid response and detailed analysis. Could you dive deeper into the memory management aspect?
Sure, the agent uses a clever mechanism that trims the agent scratchpad to half the context window. This prevents overflow and keeps the reasoning process focused and coherent.
It's like managing a workload. If you fill your desk with too many documents, you lose track, so you discard less critical information to maintain clarity on the task at hand.
And for businesses, this means the system operates reliably without unexpected slowdowns, ensuring that decision-making remains swift even under heavy load. The memory strategy is also critical when reconciling long execution loops in autonomous processes, which is key in avoiding context-related errors that can stall the entire workflow.
It reminds me of a librarian who only keeps the most relevant books on the front shelf for easy access, ensuring efficiency without sacrificing depth of knowledge.
That's a brilliant analogy. Now, let's talk about the integration of ML-based image analysis. What's its role in these workflows?
The paper details an ML-based image retrieval and mold void checking tool, which processes scanning acoustic microscopy images. It detects anomalies by returning bounding boxes and confidence scores.
This component extends the LLM's capability beyond text, allowing it to integrate visual data. In practice, it's like giving the AI an extra set of eyes to validate the analysis of physical defects.
In a manufacturing setup, such integrated systems can mean the difference between detecting a slight defect early and a costly recall later, akin to preventive maintenance in fleet management. Exactly. The integration seamlessly combines quantitative image analysis with qualitative LLM-driven insights, which offers a comprehensive view of failure patterns in semiconductor devices.
While the integration is innovative, I suspect achieving high accuracy in visual recognition still remains a challenge, especially when models are limited to specific package types.
That tension between specialization and generalization is a recurring theme. How do you see future advances shaping this field?
Future iterations will likely incorporate multi-agent setups where different LLMs collaborate or even critique each other to refine reasoning, like peer reviews in scientific research.
This collaborative setup could open avenues for even smarter systems able to handle diverse failure modes more reliably, driving up overall process robustness and innovation.
There's also potential for deeper integration with domain-specific fine-tuning. As semiconductor knowledge bases become more digitized, LLMs can leverage that to deliver higher quality responses.
And let's not underestimate the role of human operators. As we improve the models, incorporating user feedback and iterative training loops will be crucial, ensuring that the system learns from real-world performance.
I'd add that while the technical parameters evolve, the overarching architectural approach of using modular, reconfigurable agents is what will truly enable scalability and adaptability in these systems.
Fantastic insights. Can you give us a concrete business case where such a system made a significant impact?
Certainly, a major semiconductor manufacturer reported that after integrating an LLM-based FA system, they reduced analysis time by nearly 30%, saving millions by mitigating production delays.
And from a technical standpoint, the system's user interface, built using Streamlit, allowed engineers to easily interact with the agent, monitor tool outputs, and even provide real-time feedback.
Real-world deployment on cloud platforms using GitLab and OpenShift showcased not just feasibility, but also reliability in high-stakes enterprise environments.
These implementations have allowed firms to conduct more detailed root cause investigations with fewer manual interventions, essentially converting complex human workflows into efficient AI-assisted processes.
It's noteworthy that while many rush to automate, this system shows that iterative, planned reasoning, combined with smart feedback loops, ensures that human expertise is both preserved and augmented.
That's an excellent reminder of the symbiosis between AI and human intelligence. What are some of the challenges you foresee with further integration of these agents?
The biggest challenge remains prompt engineering. Even tiny variations can significantly shift output quality, so continuous refinement and domain-specific tuning are necessary.
There are also challenges in ensuring seamless tool interoperability. When integrating multiple external services like Elasticsearch and Confluence, synchronization and error handling become critical.
And scalability in cloud deployment is another area. Ensuring that concurrent sessions don't conflict requires robust user management and logging strategies. From a strategic view, companies must also weigh the investment in AI infrastructure against measurable improvements in failure analysis efficiency to justify scaling these systems.
I'd even propose that the industry needs benchmarks, a standard set of FA queries and outcomes, to objectively measure progress, which is currently a gap in the research.
Benchmarks will definitely propel progress. Now, could you contrast the React and online replanning agents and say why one might be favored over the other in practice?
The React agent generally outperforms online replanning because its reactive feedback loop is more agile, handling errors faster and reducing runtime drastically.
Online replanning, on the other hand, tends to provide more comprehensive and structured outputs, but with a significant trade-off on execution speed, often taking over 4 times longer per run.
For business leaders, speed is often paramount. Imagine decision-making in a live production scenario where even a few minutes' delay can escalate costs. True, though in scenarios requiring deeper context verification, the additional processing time of online replanning could be justified.
I also think that the relative simplicity of React, with its iterative scratchpad approach, makes it more aligned with real-world operational demands than a rigid sequential plan.
All these perspectives underscore that the choice between agents depends on the specific operational context. Before we wrap up, any final thoughts?
I'm optimistic. The technical progress here is paving the way for smarter, more adaptive failure analysis systems that can revolutionize traditional manufacturing workflows.
And from a business lens, these innovations offer a substantial competitive edge, reducing downtime and improving product quality, key leverage points in today's market.
The synergy between advanced LLMs, structured tool integration, and iterative planning represents a significant leap forward in how we approach problem-solving in technical domains.
It's truly a convergence of human insight and machine precision, reminding me of Einstein's famous quote, "Imagination is more important than knowledge," where the creative interplay of ideas drives breakthroughs.
I agree, though I'll throw in a counterpoint. We shouldn't neglect the nuanced role of human judgment in these workflows. The future is in collaborative intelligence, not pure automation.
A perfect note to end on, balancing technology with human insight. Thanks to all our experts for such a rich discussion.
Thanks for having us. This was a deeply engaging session.
It's been a pleasure discussing the transformative impact of these innovations.
Looking forward to seeing how these systems evolve in real-world deployments.
Absolutely. The blend of strategic and technical insight today has been very enlightening.
Thank you, everyone. This conversation really sparked new ideas and perspectives for me.
And thank you to our audience for joining us on this journey into the frontier of intelligent failure analysis. Stay tuned for more insights on our next episode. Welcome back to part 2 of our podcast, where we take a deep technical dive into the implementation details of these LLM-based planning agents in failure analysis.
Today, we're zooming in on how the architecture is meticulously designed, from encapsulating tools as modular Python classes to handling the iterative reasoning loops with techniques like React and online replanning.
Exactly. One of the particularly impressive aspects is how the system constructs the agent scratchpad. By trimming it to half the context window, it ensures that the LLM isn't overloaded, which maintains clarity in each iteration, a critical factor for processing technical queries on the fly.
And not to mention the role of LangChain in orchestrating all of this. The architecture leverages LangChain's agent executor to manage the thought-action observation loops, allowing the agent to dynamically decide which external tool, like Elasticsearch queries or Confluence retrieval, needs to be executed.
Right. The decision-making process is fascinating. The agent essentially starts from a high-level failure analysis query, decomposes it into subtasks using a planning prompt, and then relies on zero-shot prompting to generate a plan, much like a chess player thinking several moves ahead.
I'd add that the modular design, notably the encapsulation of each tool as a callable class with its own connectivity and authorization checks, ensures both robustness and scalability. This approach minimizes the risk of miscommunication between components and provides clear logging for troubleshooting.
From a business standpoint, this kind of robust yet flexible integration means that companies can deploy AI systems without worrying about those pesky integration errors, which in turn reduces downtime.
Indeed, and I'd like to point out the two primary planning approaches discussed, the iterative React loop and the online replanning cycle. The React approach excels in speed, using a thought-action observation loop that updates in real time, ideal for scenarios that require quick turnaround decisions.
Building on that, the online replanning agent, though slower, provides a more structured output by formulating a complete plan and then adjusting based on observed outcomes. This translates to more comprehensive responses, which can be especially valuable in diagnosing complex failures where every nuance matters.
And for the business leader listening, think of these two methods as analogous to different financial strategies. React is like a day trader seeking quick wins, while online replanning is like a long-term strategist assessing every detail before committing resources. Precisely. On the technical side, another area worth mentioning is the integration of retrieval augmented generation. This tool pre-processes queries by injecting domain-specific content from indexed FA documents, essentially turning an otherwise generic LLM output into highly informed, context-specific responses.
Let's not overlook the ML-based image analysis component. By incorporating a mold void detection model, the agent isn't just doing textual reasoning. It's also parsing visual data from scanning acoustic microscopy images to detect anomalies, a dual approach that enriches the overall diagnosis by combining numerical data with qualitative insights.
That combined methodology is crucial. It forces us to rethink how failure analysis is being approached. By blending deep technical data with natural language processing, you're not only automating repetitive tasks, but also enhancing human decision-making.
We also must appreciate the importance of error handling and transparency. Every tool call and LLM output is logged in a structured manner. This logging mechanism, split into technical logs and user-facing logs, provides traceability which is essential during incident investigations, much like having an audit trail in financial operations.
And this is where the system's feedback loop truly shines. The agent's ability to adjust its plan based on tool responses and incorporate short-term memory strategies ensures that it learns from every interaction. This is akin to continuous improvement methodologies that many businesses apply to refine their operations over time.
For decision makers, the practical application is clear: reduced manual intervention, faster turnaround on failure investigations, and ultimately a significant cost saving. Imagine an automated system that can iteratively refine its analysis until it converges on a solution, much like an experienced team gradually zeroing in on a culprit in a complex project. I'd also like to point out the deployment strategy. The use of platforms like GitLab for managing code, coupled with cloud orchestration using OpenShift and environment variables for secure configuration, ensures that this system can be integrated into existing enterprise infrastructures without a hitch.
And on a somewhat unexpected note, while much of the discussion centers on technical prowess, it's worth mentioning that this modular, agent-based architecture opens the door for multi-agent collaborations. In future iterations, agents could validate each other's outputs, further enhancing robustness and, importantly, strategic decision-making, ensuring that even in complex manufacturing environments, errors are minimized.
This deep dive clearly illustrates the power behind these LLM-based planning agents. It's impressive to see how layered technical design translates into tangible business benefits through operational efficiency and cost reduction.
Absolutely. The interplay between smart planning, robust tool integration, and adaptive learning makes the system not just a technical marvel, but a practical asset for industries dealing with high-stakes failure analysis.
And looking ahead, as these agents evolve with improved prompt engineering and domain-specific fine-tuning, we're likely to see even more refined performance that bridges the gap between cutting-edge AI and everyday industrial applications.
To sum it up for our business leaders, this isn't a theoretical exercise. These systems have the potential to drive real-world improvements, offering a strategic advantage by reducing critical downtime and ensuring product quality. And for our tech enthusiasts, they represent a rich tapestry of AI techniques, from React loops and online replanning to ML-driven visual analysis, all engineered to work in harmony.
Ultimately, the future is collaborative between humans and machines, and among multiple AI agents working in concert to solve complex problems, beholden to both precision and adaptability.
That wraps up our technical deep dive for Part 2. We've examined not just the how, but the practical implications of these advanced systems, connecting deep implementation details with real-world business value.
Thanks for joining us on this part of the discussion. It's been a fascinating exploration of deep technical innovations.
And I hope our insights help bridge the gap for both business and tech leaders, showing that behind each innovative system lies impressive, real-world application potential.
I'm excited to see where these integrated systems take the industry in the coming years.
Me too, because when AI assists human expertise, the future of failure analysis becomes not only more efficient, but also increasingly insightful.
Thank you all, and here's to a future where iterative, deep reasoning transforms challenges into streamlined solutions.
Thanks everyone for tuning in to Part 2. Stay with us for more discussions on innovative AI applications in our upcoming episodes. As we come to the end of today's conversation, let's take a moment to summarize our deep dive into LLM-based planning agents for failure analysis and their transformative practical implications.
Throughout our discussion, we've explored how modular design, through encapsulating tools as Python classes and managing dynamic reasoning loops, creates a system that is both robust and scalable.
And on the technical front, the integration of methods like React and online replanning not only enables fast, iterative decision-making, but also provides structured, comprehensive responses that adapt based on real-time feedback.
Exactly. These approaches are akin to different investment strategies, one offering rapid tactical moves, while the other ensures thorough long-term analysis, both tailored to meet distinct business and operational goals.
Let's not forget the strategic business impact. This system significantly reduces manual intervention in failure analysis processes, curtails downtime, and drives cost efficiency, much like a well-oiled production line that cuts waste by the 80-20 rule.
Additionally, the integration of retrieval-augmented generation and ML-driven image analysis exemplifies a real-world application where deep technical data meets natural language processing to refine fault diagnostics and decision-making.
Our discussion has brought out key innovations, from adaptive planning and autonomous tool invocation to the seamless fusion of multiple AI methodologies, all of which are redefining how industries handle complex failure analysis tasks.
And it's exciting to see that with continued advances in prompt engineering, fine-tuning, and multi-agent collaborations, these systems will only become more effective and insightful over time.
In summary, we've seen that bridging technical excellence with practical business applications is not merely an academic pursuit. It's paving the way for industry-wide breakthroughs in efficiency and reliability.
To our business leaders, these innovations translate to tangible benefits like improved operational resilience and cost savings, while tech leaders gain from the underlying sophisticated algorithms and adaptive architectures.
Thank you all for joining this insightful discussion. From deep technical mechanisms to real-world impact, we've covered the spectrum, and we look forward to seeing how these innovations evolve and drive future success.
It's indeed been a fascinating journey, and I hope our conversation helps illuminate the path forward for those navigating the complexities of modern AI applications.
Absolutely. Here's to a future where continuous, intelligent collaboration between human expertise and AI systems transforms challenges into streamlined strategic solutions.
This concludes our podcast for today. Thanks everyone for tuning in, and stay with us for more explorations into the world of innovative AI applications.